Alright, so for our second video for today's lesson, we are going to look at percent yield. And so far, what I want to point out to y'all is that what you've been doing in all of your stoichiometry calculations, every time that you have calculated an amount of a product, whether it was moles of the product or grams of the product, what you were doing was solving for the theoretical yield of that particular product. So the theoretical yield is the maximum amount of that particular product that can be produced from that particular reaction and from that amount of reactants. Now, in the real world, most chemists don't usually make the theoretical yield. There's some reasons for that, such as gases that may escape the reaction, or some intermediate products that are made, but that's beyond the scope of this course. What you need to understand is that the theoretical yield is never actually made. But you do have something that's called the actual yield. So this is going to be a smaller, a lesser amount that is truly made, actually made. Now, the actual yield must be given to you in the problem. You cannot calculate the actual yield with the information that's given to you in the problems you have in this classroom. Now, from these two amounts, the theoretical yield and the actual yield, you can calculate something that's called the percent yield. This is done much the same way you determine your percent grade on a test. The formula for percent yield is actual yield divided by the theoretical yield. So for a test, you would say the amount of points you earned versus over the total amount of points that were on the test times 100. So now we're going to mix doing some stoichiometry problems and with then using that information to help us determine the percent yield for a particular reaction. All right, let's look at this example problem. And the question says that one method of preparing chlorobenzene, which is C6H5Cl, is to react benzene, C6H6, with chlorine as seen in the following equation. When 36.8 grams of benzene react with an excess of chlorine, the actual yield of chlorobenzene is 38.8 grams. What is the percentage yield of chlorobenzene? So the first things first, always, is the equation balanced. And as you look at it, you'll see that your carbons are balanced. You have 6 on either side. Hydrogens are balanced. You have 6 on either side. And the chlorines are balanced. So now let's go about writing our knowns and unknowns. So first thing I'm going to do, and give it a color, and let's go ahead and do the blue. All right, so our knowns and our unknowns for this. Our known is that we have 36.8 grams of benzene. And notice that we are told that the benzene is our limiting reactant. How do we know this? Because it tells us that chlorine was the excess reactant. Okay, so we're just kind of working off of what they are telling us and using that information to infer what the limiting reactant is. And what are we solving for? We are trying to determine the percent yield of that chlorobenzene. Now, in order to do that, we're also going to have to determine the theoretical yield. Okay, so I'm going to go ahead and write that in here as well. What is the theoretical yield for chlorobenzene. And that's where the stoichiometry is going to come in. We're going to do a stoichiometry problem that goes from the 36.8 grams of benzene to a theoretical yield grams of the chlorobenzene. So the next thing that we are going to do is solve for our molar masses of our known and our unknown. So let's start with the benzene, which is made up of carbon and hydrogen. 6 chlorines and 6, carbons and 6 hydrogens. And carbon is 12.01, hydrogen 1.01. And we get 78.12 grams per mole. All right, now let's do the chlorobenzene. So once again, carbon, hydrogen, and now we have a chlorine. We got 6 carbons, 5 hydrogens, 1 chlorine. 12.01 off the periodic table for carbon, 1.01 for the hydrogen, and 35.45 for chlorine. All right, so the total amount of carbon is 72.06, the total amount of hydrogen, 5.05, and the total amount of chlorine is 35.45. All right, I'm going to add that up, and we get 112.56. All right, now let's go ahead and set up our stoic problem. All right, so I'm going to scroll this up just a little bit more. Okay, so we are going to start off with 36.8 grams of benzene. And we're going to go ahead, because it's in grams, we have to convert those grams into moles of benzene. And we're going to do that with the molar mass. So that is 78.12 grams we have 78.12 grams of benzene for every 1 mole of benzene. Now that we have benzene in moles, now we can convert that into, now we can do the mole ratio so we can see how much benzene to chlorobenzene. So we have every 1 mole of benzene, we're going to produce 1 mole of chlorobenzene. And once again, where do those numbers come from for this part of the train tracks? Our balanced equation, okay? Those understood ones, coefficients of ones that are there in the reaction. Okay, so now that we have gotten to moles of chlorobenzene, now we can do that into grams of chlorobenzene. So we're going to do that with the molar mass, 1 mole C6H5Cl, and we're going to get 112.56 grams. That's our molar mass. All right, so if you put all of that in your calculator, punch and crunch, you're going to come up with 53.0 grams of chlorobenzene. Now, once again, don't forget about sig figs. So we have 3 sig figs in our final answer, just like we have 3 sig figs in our given. All right, so this is how much chlorobenzene will be made when you have 36.8 grams of benzene. Now we need to go ahead and do the percent yield. Okay, so remember, percent yield is going to be the actual yield over the theoretical. And all of that is going to be multiplied by 100. Now don't forget, your actual yield should always be smaller than your theoretical yield. If you come up with a theoretical yield, when you do all your stoichiometry, and you find that your theoretical yield is smaller than the actual, bells need to go off, sirens need to go off in your head. You did something wrong. There's something either not set up right in your problem, or you've punched and crunched incorrectly, and you need to try to rework your stoichiometry problem up here. But if your actual yield is smaller than your theoretical, remember, theoretical is the maximum amount that you can make from your reaction and the amount of reactants that you have, and the actual yield is what is the reality, what is actually made due to losses for one reason or another. So let's put our numbers in. So percent yield is going to be, let's see, 38.8 over 53.0. And once again, don't forget to multiply it by 100, and we find that we get a percent yield of 73.2%. And as always, box your final answer. So that's how you solve percent yield. Now, what I thought I would do now is to go ahead and work through the first problem on your worksheet so that you can see all of this put together now. So now we're going to be looking at being able to find limiting reagents, excess reagents, theoretical yield, percent yield, everything. We're going to put it all together. All right, so put lots of space in here. And let's see what we can do with that. All right, so we have 170 grams of ammonia, and it's reacting with 300 grams of sodium hypochlorite. The experiment yields 124.3 grams of N2H4, and you're given the reaction. Let's look at the reaction real quick and make sure it is balanced. It does look good, looks like everything is balanced. So let's go ahead and write out our knowns. So we have lots of knowns in this problem. We have 170.0 grams of ammonia. We have 300 grams of the sodium hypochlorite, and we're also given in the problem the experimental yield. That experimental yield, ladies, that is the actual yield, okay? So the actual yield is going to be 124.3 grams of N2H4. All right, now that we have all of that done, let's go ahead and I'll do it in a different color. Let's go ahead and solve the molar masses for the ammonia, the sodium hypochlorite, and the N2H4. Okay, so we have 3 different molar mass problems that we need to do. All right. And we have 3 hydrogens. Nitrogen is 14.01. Hydrogen is 1.01. All right, so ammonia is going to equal 17.04. All right, so that is the ammonia. And then let's do the sodium hypochlorite next, which is Na, and chlorine and oxygen. Now we have one atom of each of these in this compound, so we are just going to go straight to our periodic table, use those numbers, add them up. So sodium is 22.99, chlorine is 35.45, and oxygen is 16 even. So we add that up and we get 74.44. And that is our sodium hypochlorite. All right, last but not least is going to be the N2H4. So that's going to be, once again, and we have 2 nitrogens, 4 hydrogens, 14.01, 1.01, and 28.02 is going to be added to 4.04 so that we can get 32.06. Okay, now that we have that done, let's go ahead and do our stoichiometry problems. So let's go ahead and start with the ammonia. So we have 170, and you know what, let me bring that down a little bit. I think it's a little too high. All right, let's get started again. So we have 170.0 grams of ammonia. Okay, so next we're going to do the molar mass of ammonia, which is going to be 17.04 grams in 1 mole. And then we're going to do our mole ratio. So we're going to have 2 moles of ammonia, and we're going to have 1 mole of N2H4. Once again, where are these numbers coming from? They're coming from our balanced equation. And now we're going to do our molar mass of the N2H4. And our molar mass is 32.06. All right, and we're going to punch and crunch, and we are going to come up with 159.9 grams of N2H4. All right, well, that was fun, and we get to do it all over again. Let me see if I can get a little more space. All right, and let's squeeze in our next stoichiometry problem. So now we're going to do the stoichiometry, and here, I'll do it in the black. Now we're going to do the stoichiometry for the sodium hypochlorite. So we have 300 grams of NaClO. All right, now we're going to do the molar mass. 74.44 grams. That way you can see my numbers and where I'm getting them from. All right, so there's a 74.44 grams of the sodium hypochlorite in 1 mole of that substance. Now we're going to do our mole ratio. So we see that we're going to have 1 mole of NaClO for every 1 mole of N2H4. Once again, our numbers are coming from our coefficients in our balanced equation. And next we're going to do the molar mass of N2H4. And that's 32.06 grams N2H4. Punch and crunch, and you're going to get 129.2 grams N2H4. Okay, so when we compare our numbers here, we see that this is our smaller number. So that is the theoretical yield of N2H4. And then our limiting reactant is going to be the sodium hypochlorite. So let's scroll down a little bit more and let's answer these questions. So how many grams of N2H4 can be produced? The maximum number that can be produced is 129.2 grams of N2H4. What is the excess reagent? That is going to be the ammonia. And you know what I'm going to do? I'm going to put some space in here. So it's a little easier to read. All right, the limiting reagent, that's going to be the sodium hypochlorite. The actual yield, once again, you got to go all the way up to the top of the problem, and it tells you the actual yield is 124.3 grams of N2H4. The theoretical yield, that's going to be this number here, okay? That's also our theoretical yield. So the maximum amount of grams of N2H4 that can be produced is also our theoretical yield. So 129.2 grams of N2H4, percent yield. Okay, so now we are going to take that 124.3 over 129.2 and then multiply that by 100, and when you punch and crunch you're going to come up with 96.21%, and that is your percent yield. All right, so that is how you work out the problems on your worksheet for today's work. If you have any questions, as always, you can email me, you can Skype me, and I will talk to y'all tomorrow.